In this video, we'll look at the review for the Unit 2 test, which covers all of Chapter 3 and Chapter 4. And I have the questions in order on the review of the sections in which I overviewed them in the video lectures. So here for the first question, it's kind of a 2-for-1 type question. It looks at covering the information that was addressed in Chapter 3, Section 1 and Chapter 3, Section 2. And so here we see that we have a grouped frequency distribution identified by the class and the frequency, and we want to approximate the sample mean, find the variance, and also the standard deviation given the following frequency distribution. So hopefully we know, or we kind of recall, that to find the sample mean from a frequency distribution, because we don't know the original data set, we're estimating it. So we have to find the sum of the frequencies times their midpoints and then divide that by the total sample size. So we already know the frequency, right? We're given that information, but we have to find the midpoint, and it's the midpoint of the class. It's either the midpoint of the class or the midpoint of the class boundary. So this is a skill or something that we would have talked about in the first unit that's carried into the second unit. And to find that midpoint, we know that if I take 0 plus 14 divided by 2, I get 7. And if I take 15 plus 29 divided that by 2, I get 22. And we kind of repeat that process, and we get the midpoints for each one of the classes. So this is the value in the middle of each class. Now, in order to utilize this formula, I need to find the sum of the frequency times the midpoint. And right now I don't have that. I have the frequency separately. I have the midpoint separately. Now I need to multiply each frequency times the midpoint for all of them, and then I can find that sum. So we go through and multiply 11 times 7, 8 times 22, 10 times 37, and on, and then we get those values. And now that I have the frequency times the midpoints, I can add these together to get the sum that I need for my estimated sample mean. So that's a sum of 2029, which represents the information in the numerator, and the denominator is the total frequency of all the values that's represented in this grouped frequency distribution. So we got to find that information. So if we add all the frequencies together, we get 52, and that means my average, or my estimated sample mean, is 30.02. So that's how we remind ourselves how to find an average from a frequency distribution. The problem also wants us to find a variance and a standard deviation. So we know that the variance in this formula, the sample size multiplied by the sum of the frequencies times their midpoints squared, or times the sum of the frequency times the square of the midpoints, minus the sum of the frequency times the midpoints, and that quantity is squared. So this value we actually already have thanks to the sample mean. That's this number here, the 2029. We already have that number. And then again, the total sample size times the total sample size minus 1. So this is how we calculate the variance from a group frequency distribution. And then to get the standard deviation, the relationship there is just take the square root. So we have most of the information we need to find the variance just by finding the sample mean, because we have this information over here. We know what n is. The only thing that we need to find is the frequency times the squares of the midpoint, and sum that information, and then we'll have everything we need to calculate the variance. And subsequently, we'll have everything we need to calculate the standard deviation. So this value, this first value, 539, that would be the frequency of 11 times 7 squared. So that's where the 539 comes from, and I'll show you that here. If I take the 11 times 7 squared, that'll give me 539. And then we can continue that process to find the rest of the values, taking the frequency column times the midpoint column squared. And we need this information so that we can satisfy this part of the formula. And we get the sum of that value, which is 105,283. And now we have the information necessary in order to find the variance for this distribution. So we know that we take the sample size times the number in green minus the number in orange squared divided by the sample size times the sample size minus 1, and that value is the variance. So this 512.02, that is my variance value. Now, to get the standard deviation, we just take the square root of the variance. So it's very important that we find the variance correctly, because the standard deviation is dependent on that variance value. If the midpoints are off, then the average will be off. If the frequency times the midpoints are off, then the average will be off and the variance will be off. So it's very important that we are attentive to the details here when we calculate these values. So the standard deviation, if we kind of remind ourselves, this is the amount, this is what we expect the values within each class to typically vary from the average value. So that's typically what we see is the typical spread in the distribution, the 22.63. So if we were to interpret that number, we could say that the values in the frequency distribution, they typically vary by 22.63 from the mean of 3902. So if we actually knew what each value was and we compared those values to the average, then for the entire distribution, they would typically be about 22.63 units away from the mean, either above or below. So that is a relatively higher standard deviation, but we look at the distribution and it's pretty evenly spread out, right? We go from 11 values to 8 values to 10 to 9 to 14. So it's a pretty even spread how the numbers are in the distribution. If we saw most of the values clustered towards the middle, so maybe this was like only 3 numbers in the first class and then 5 numbers in the second class and then 40 numbers in the third class, and then it started to taper off, we would expect a lower variance or a lower standard deviation because it wouldn't be as spread out. Because these are kind of evenly spread out within each one of the classes, then we have a higher standard deviation. So that's question number 1, covers 3.1 and 3.2. And we kind of transition and we look at question 2, which covers chapter 3.3, the measures of position that indicate which student has a higher z-score. Well, if we recall, the z-score is the number of standard deviations, a value, so the x is away from the mean, in this case the sample mean x bar. So the z-score formula is the value minus the mean divided by the standard deviation. In this case, we look at x minus x bar divided by s. So x would be the value, x bar is the sample mean, and s is the sample standard deviation. And we just utilize that formula to help us convert these two numbers into a z-score so we can compare their relative position. Because right now, the 46 comes from a different set of data than the 70, and we really, although we know that the 70 is higher, a higher test grade, it may not be relatively higher compared to the 46 because of the overall average or because of the sample average. Because that does take into an effect of the z-score and also the standard deviation from the data set. So when we calculate the z-score for art, it's 46 minus 50.5 divided by 5.2. That's about negative 0.87. We look for theater, 70 minus 75.1 divided by 7.3. That's about negative 0.7. And so this is a higher relative position because it's less negative. It's closer to the average than this number is. This one is far lower. So theater would have a higher z-score relative to the art major. And I don't want you to think that it's always going to be the number that's larger. In this case, it just happened to be larger. There could be an instance where art could have had a higher z-score. It all really depends on what's the sample mean and what's the standard deviation. So a larger So now let's look at chapter 3.3 and 3.4. This is where we looked at in chapter 3.3. We actually talked about outliers in chapter 3.3. And then in chapter 3.4, we looked at the 5-number summary when we made the box plots. So this is a good problem to kind of touch on all those bases. And when we looked at the last 2 sections in chapter 3, again, outliers talks about measures of position. where data is located, or where the position of data in a data set. So we talked about quartiles and percentiles, and then the 5-number summary are 5 numbers that help us sum up the data and also divide the data into different quartiles as well. So those two sections are interrelated. The first thing we want to do is just remember what is the 5-number summary, and that is, we want to be able to identify these 5 things: the minimum, the first quartile, the median, the second quartile, or actually the third quartile. So let me fix that, because the quartile number 2 is in fact the median. So this should be that should be the third quartile, and then the maximum. So these are some things that we want to be able to identify for the 5-number summary. In order to do that, we have to make sure that our data set is in order from least to greatest. And more or less, this is already in order for us, so least to greatest, so we don't have to worry about that. After it's in order from least to greatest, then we can go ahead and look, well, what's the minimum value? And that's really easy to identify. It's 7, right? It's the smallest number in the data set. The Q1 we have to wait to find, the median we'll wait to find, the Q3 we'll wait, and the max we know is 43. All right, that's the largest number in our data set. The next number we would want to find is the median value. We want to be able to divide the data into 2 parts, so the lower 50% and the upper 50%, because that will enable us to find the first quartile and the third quartile. And so we look, and there are 1, 2, 3, 4, 5, 6, 7, there's 8 data values. So the median number is actually in between the 2 middle numbers. And so the median values are 28 and 32. And so we want to find the average of those 2 numbers. Add those 2 numbers together and divide by 2, and that gives us a median of 30. And so that means this number 30 separates the data set. Anything below 30, so these 4 numbers, 7, 11, 21, and 28, that's the bottom half. Anything above 30, 32, 33, 34, 43, that's the upper half. And the first quartile is the median of the lower half. So out of these 4 numbers in the bottom half, from 7 to 28, the median is between 11 and 21. So we add that together, find the middle is 16. So that's the median. That's the median of the lower half. So this is the 25% cutoff. Anything below that is in the bottom 25%, and then anything above that, so every number above 16 is in the upper 75%. I guess we can say it that way. And then we do the same thing for the third quartile. So this is our 5-number summary. These 5 numbers, 7, 16, 30, 35, and 43, are able to kind of help us summarize the data and then divide it into different quartiles. So each set of numbers in between these values are different quartiles. So 25%, 25%, 25%, 25%. Now, for outliers, we want to look at 2 things. We want to be able to find the interquartile range, and we also want to, after we find the interquartile range, we want to be able to use these 2 formulas. So the first quartile minus 1.5 times the interquartile range. That helps us find the lowest extreme value that we expect to be within the data set. And then the third quartile plus 1.5 times the interquartile range. And that helps us find the highest extreme value that we expect to be in the data set. So we know the IQR is Q3 minus Q1. So subtract those 2 numbers. That's the middle 50% of the data. And then now we just use that value to substitute into our formula. So here, Q1 is 16. So minus 1.5 times 19. And that gives us a negative 12.5. And what we look at is there any value below that? This is the lowest number that we expect in our data set for there to be no outliers. If there's a number lower than that, then there's an outlier. And the lowest number is 7, so it's not an outlier. And then we did the same thing for the upper part of the data, Q3 plus 1.5 times the IQR, and we end up getting 63.5, and we can see that if there is a number bigger than that, then that number is too extreme for the data set, because this is the largest number that we expect based on the information provided, and the biggest number is 43. So there is no outlier there either. So we can conclude that no outliers in the data set, since there are no values more extreme than the negative 12.5 and the 63.5. So those three questions kind of sum up what we talked about, or what I talked about in the video lectures for chapter 3. That's what you can expect to be able to do on the Unit 2 test. For chapter 4, we get into probability. So the remaining of the questions are all about probability, and we go through and kind of discuss different ways to approach probability type questions. So I didn't include questions for 4.1 because 4.1 was just basic understanding of probability, and that's included within every question because we calculate probability the same way. The number of outcomes in our event divided by the total number of outcomes in the sample space, and we look at that regardless. So 4.2, here we look at, and this would be more reminiscent of empirical probability because we have a table of values, like a frequency table. So it's a survey of over 34,000 homeowners, how many pets they owned. So they asked this many people how many pets they owned. The results were as follows. What's the probability that the sample homeowner has at least one pet? So we have to kind of think about, what does the word at least mean? At least one means they can have one or more. All right, so that's the first thing we want to be able to determine what that means. And then what we look at, if they can have one or more pet, in a probability standpoint, if I write my probability statement, is the probability that they have at least one pet is the same as saying the probability of one pet, or two pets, or three pets, or four pets, or more. And so this is what we want to be able to find. And we have to remember that the word or tells me I have to add the probabilities together. So if we look at our table here, here's one or more. So any of these four values here would represent the outcome our desired outcome. So we add that information together, and we get 28,287 out of the total 34,407, and that gives us our probability of about 82%. And that's a highly likely event to occur. If we were to select a homeowner at random, they would have at least one pet. Most of the individuals in the distribution have one pet. Now, another way we can look at this is a complementary event, right? The same way that we look at the probability that they have more than one pet, we can say 1 minus the probability that they have less than one pet, because that would be a complementary event, right? A homeowner that has more than one pet plus a probability the homeowner has less than one pet would be 100%, because you either have one or more pets or you have less than one pet, which is none. So that would be a complementary event that we would have. And for us to calculate that, we simply would just look at, well, 1 represents 100% minus the probability that someone had no pets, which would be 6,120 out of the total, which gives us the same answer as before. So those are two kind of different ways to approach finding that probability. Now, the next question we want to think about, this is where we get into mutually exclusive and non-mutually exclusive events. So in a fish tank, there are 15 goldfish, 6 angelfish, and 18 guppies. If a fish is selected at random, find the probability that the fish is an angelfish or a guppy. So we have to remember the word, anytime we see the word or, it tells us that we're adding the probabilities. It increases our likeliness of that event to occur. So this is my little statement. I want the probability of an angelfish or a guppy. And hopefully we are aware that these events are mutually exclusive. You don't have any angelfish that are also guppies, so they don't overlap with each other. So that means you can either be an angelfish, or you can either get an angelfish or you can get a guppy, and they have no mix, they have no overlap. So this is what we consider a mutually exclusive event. So we just look at the probabilities of each event and we just add them together. So what's the probability of an angelfish? What's the probability of a guppy? Well, we first find the total. There's a total of 39 fish, and angelfish 6 out of 39, guppies 18 out of 39. So my probability 8/13 or 0.62, which is somewhat likely, right? A likely event is 0.75. This is getting close to 0.75, so that's a somewhat likely event. So that's an example of what we look at for mutually exclusive. Now, an example of non-mutually exclusive, still 6.2, and still the word or, says if a single card is drawn from an ordinary deck of cards, what is the probability of drawing a black or a king? Well, we have to, although the table's not here, that we had in the homework questions from those lecture videos, we kind of think about what the sample space might look like. And my probability statement is probability of black or a king. So we think, well, in all the black cards, are any of those kings? And then in the 4 kings, are any of those black? And of course, yes, there's 2 black kings in all the black cards, and the kings have 2 black cards. So there's definitely overlap there. So this would be not a mutually exclusive event. So we have to take care of the overlap. So when I start to write out this statement, the probability of black or king starts out just like the angelfish or guppy. The only difference is because there's overlap, we have to take care of that overlap. So this part is the same. Probability of black plus probability of king minus, well, where do they have overlap? Well, wherever there's a black and a king is where they overlap. So we think about, well, in the deck of cards, how many of the cards are black cards? Well, half of the deck are black. And then how many of them are kings? Well, 4 out of the 52 are kings. And how many of the cards in the deck are a black and a king? Well, it's 2 of them. And so I'm going to change that to 26 out of 52 instead. So we have a common denominator. So we look at, in this 26 cards, 2 of them are also kings. In these 4 cards, 2 of them are also black. So we're counting them twice. Since we're counting them twice, we take one of those instances, one of the 2 out, so that we only count it once over here. So then we can get our resulting probability, which is 28 out of 52. And of course, we always want to reduce that or write the decimal equivalent. So 7/13 or 0.54. Now that number is higher than equally likely. So it's getting, it is more or less getting to the somewhat likely range that it either will be black or it will be a king. So number 7, we look at this one, and I put the section here so you can, the section won't be on the test, but at least you can have an idea of how the wording changes. In the previous probability questions, it mentioned the word or, and then in number 7, number 8, we no longer see the word or. So we want to kind of be cognizant or aware of that change. 4.3 is where we got into independent and dependent probability. So a coin is tossed 5 times, find the probability that all 5 tosses are tails. What does that look like as a probability statement? So I want the probability that I have 5 tails in a row, which means the first one is a tail, and the second one's a tail, and the third one, and the fourth one, and the fifth one. That the word and is implied because I want all 5 of them to be tails. So we can't really think of this as an or statement because it needs to be all 5 in a row. Tail, 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 tail. So the word and, that lets us know we want to multiply the probabilities together because it's and is very specific, and we don't want the chances are not that high because it needs to be all 5 back to back in a row. So we look at it is an independent event because me flipping a tail the first time has no effect on any subsequent flips. So our probability of a tail times probability of a tail 5 times, where we know there's only 2 choices. You can either have a head or you can have a tail. So each probability is 1/2. So it's just 1/2 times 1/2 times 1/2 5 times, or 1/2 to the 5th power, which is 1/32, which is a very, very unlikely event, right? There's a 3% chance that if we were to flip a coin 5 times, all 5 times it would be tails. So this would be an independent event. The first outcome does not affect the second outcome. The probabilities have remained the same throughout. And with independent and dependent is when we use the word and. With mutually exclusive, non-mutually exclusive, we use the word or. So that's something for you to remember. Now if we look at a dependent event, so in a 2nd grade class containing 12 girls and 11 boys, 2 students are selected simultaneously at random to give out math papers. What's the probability that both are girls? So when we think about this particular question, we have to consider without replacement, right? Simultaneously just means without replacement. I'm picking one student, at the same time picking another student. The one student I picked is not going back into the group, so it changes the number of people who I have to choose from where my hand lands a second time. So without replacement is definitely a dependent quantity or a dependent statement. The first choice inadvertently affects the second choice. So the probability that a girl is chosen and another girl is chosen at the same time, so that's just girl times girl. There are 12 girls to begin with out of the 23 students, and then I pointed at one. At the same time, there's now only 11 girls to choose out of 21 students, or out of 22 students. So this is what we look at when we have dependent events, that the second probability is affected by the first one. Now, if it had been a girl and a boy, then the denominator, or it would still, the numerator would still be 11 because of 11 boys, but the denominator would also still have changed. So the numerator is only changing because we had chosen a girl first as our first immediate pick, and then also a girl as our second immediate pick. And so that's why the second one is changing because of that first outcome. But even if it were a boy, the numerator would still be 11 because there's 11 boys. We didn't choose any at first, but the denominator would always change in a dependent result. So we look at find the probability. Of course, we don't want to leave it as 132 506. That's, people might be like, oh, that's not terribly high chance, but you want to be able to represent it kind of as a decimal approximation, or at least a reduced fraction, and we get 0.26, which is again an unlikely event, right? Anything close to 0.25 is an unlikely event. On the lower side of 0.25, we get to least likely or very unlikely, and as we go from 0.25 to 0.5, we're getting to the range where it gets almost equally likely, and then we went over that is when we get to the likely events, and highly likely in the certain events when it gets to 1. Now, when we got to 4.4, we took a break from probability, and that's where we got into different counting methods. So questions like number 9, 10, and 11 have nothing to do with probability. It's just counting rules. Do you know when to use the fundamental counting principle? Do you know when to use the permutation? Do you know when to use combination? So for number 9, it says there are 3 different mathematics courses, 3 different science courses, and 2 different history courses. If a student must take one of each, how many different ways can this be done? You can either make a tree diagram here. That would work perfectly if you felt the need or the necessity to do so. But instead, we want to look at, we can do this with the fundamental counting rule. We can use the fundamental counting rule with problems like this, or with problems that we think are a permutation. Those are the 2 things we can do a fundamental counting rule for. So this particular problem, I know I can use the fundamental counting rule because essentially I have 3 different events or 3 different things that are non-overlapping. All right, I have to take at least 1 math course. I have to take 1 math course, 1 science course, and 1 history course. And so those are my 3 different events: math, science, and history. And then from those events, I have certain possible choices within each event. So there's 3 math courses I can take, there's 3 science courses I can take, and there's 2 history courses. And the fundamental counting rule tells us that as long as I know the distinct possibilities for each event, we can multiply those together, and that will be the number of different ways that you can look at your sample space. Now, if you had made a tree diagram, you would still get 18, but you would be able to know exactly what those 18 different choices are. So that's the benefit of a tree diagram. For number 10, we look at, well, for this question, it says how many different ways can a teacher select 5 students from a class of 19 students to each perform a different task? So this is where we look at, is this a combination or is it a permutation? How do I know? What does the wording tell me? Well, because I am selecting I only want 5 of the students to do the different task, but I have 19 to choose from. Since they're doing different tasks, well, that is a specific ordering, right? Each task is different. So it matters if I'm chosen to clean off the whiteboard versus if I'm chosen to put the chairs in order, right? Those are different things that I can do. So me being selected to do whiteboard duty is a different selection than me being selected to do pick up the chairs and put them in the right place duty. Versus if the teacher had every student do the same thing, I want you all to just organize the desk. Doesn't matter who you pick because we're all doing the same thing. So we have to think about this is very specific. So I use a number permutation where R is how many we're selecting or choosing from the total, and N is the total. So once you are able to identify that, you just set this up and then utilize the formula. So 19 factorial divided by 19 minus 5 factorial. Then we can simplify that as 19 factorial divided by 14 factorial. And in the lecture videos, I expanded that out. And I would expand it out in the numerator all the way to 14 factorial because I know in the denominator we can get rid of 14 factorial. And we can also remember that because we can do this as a number permutation, then you can also do this as a fundamental counting rule, right? You have 5 different slots to be filled, 5 different tasks. The first task, you can choose any one of the 19 kids. The second task, you can choose any one of the 18. And the third one, and the fourth one, and the fifth task, you can choose any one of the 15. So we could satisfy this problem using the fundamental counting rule as well and not worry about the permutation. So I wanted just to reiterate that. But we look at that there's 1,395,360 different ways for this to happen. And just kind of to re-show you how you would evaluate that. If I have in here, I'm going to do alpha y equals, so I can set up kind of the stackable fraction. And then I want 19 factorial, so math, probability, the number 4. And in my denominator, I want 14 factorial, so math, again, probability, PRB, number 4, enter. So that's the value. If I decided to use Desmos, then I do the same thing, 19 exclamation point, 14 exclamation point. So it's a little quicker to get there using Desmos. So you just got to figure out which one of those tools you want to use to help you with the calculations. Now with the number 11, since this was a permutation problem, then you're probably thinking, oh, this should be a combination problem, and you'd be right. So we look at this one. It tells us, if we kind of skim through it, the 3 chosen items need not be in any particular order. So that one's probably spells it out a lot more easier than the previous one. So it's already telling you no particular order, so there has to be just a number combination. We don't really care how the items are selected. So in a TV game show, a contestant is shown 10 particular items or 10 products from a grocery store and is asked to choose the 3 least expensive items in the set. The 3 chosen items need not be picked in any particular order. And how many ways can the contestant choose the 3 items? So again, that's the R value because that's how many we're choosing. And there's total of 10 products to choose from. So 10, choose 3, 10 factorial divided by 10 minus 3 factorial times 3 factorial. So we got to remember about this additional in factorial in our formula. Simplify that out. And I always like to show out at least expanding it out in case you're not using a calculator, so you can at least see the hand method. And I could have either written this all the way out to 3 factorial if I wanted to get rid of the 3, but I figured it saved me some hand strokes writing if I just go out to 7 factorial, so I can get rid of the 7 factorial in the denominator. And then I can just rewrite it as 10 times 9 times 8 divided by 3 times 2 times 1. Then I can use simplification skills. 9 and 3 have a common factor, and then either 10 and 2 or 8 and 2 have a common factor. So we can go through and reduce that, right? 3 goes into 9 3 times, and 2 goes into 8 4 times. So then I'm just left with 10 times 3 times 4, and that gives us 120 different ways. Now, if you thought, man, that's kind of a lengthy process, I don't want to go through all that, so you don't really have to go through all that. Again, you can use Desmos, so 10 factorial, And then really, I could just put 10 minus 3 factorial and then 3 factorial, and then it'll give you the answer without simplifying it. You want to be careful if you're not using, if you're using another calculator, that you can't create the kind of the complex or stackable fraction. You want to be very careful on how you enter your information, because I could do 10 factorial, and I'll show you the mistake, because I know students make the mistake quite frequently. Divide it by, and then you do parentheses. Let's say you do 10 minus 3 factorial. You don't want to write it out, or you don't want to simplify it. And then you do times 3 factorial. It's going to give you not 120, because what it does, it takes 10 factorial, it divides it by 7 factorial, figures out what that answer is, and then multiplies it by 3 factorial. So you'd have to group everything in the denominator in parentheses for it to give you the answer that you seek. And so for our last two questions, number 12 and number 3, they come from section 4.5, where we pick back up with probability, probability with combinations. So in this particular question, it wants the probability that both professors are chemistry. So 4 statistics professors and 6 chemistry professors are available to be advisors to a student organization. The student organization needs 2 of the professors to be advisors. If each advisor has an equal chance of being selected, what is the probability that both professors are chemistry professors? So we want to think about, in this particular question, our probability statement. We're selecting 2, right? So we want to think, what's the probability that both are chem professors? So if we write out this in words, which is what I kind of demoed in that lecture video for 4.5, in the numerator of any probability, it's always what is the desired event. And the desired event is we want 2 chemistry professors. But because we have some sort of selection process here, we have to figure out what are all the different ways that I can have 2 chemistry professors. So we want to know the number of ways to select 2 chemistry professors from 6, right? So there's several different ways you can do that. I can pick any 2 chemistry professors out of the 6 there are to choose from. And the denominator, well, that's the sample space. That's all of the ways you can select any 2 professors, so statistics or chemistry, out of 10, because there's 10 professors total. So for the denominator, it's our sample space, which is the total number of ways to select any 2 out of 10. So this is definitely a combination problem, because we don't care the order in which we choose them. We just want any 2 professors, any 2 chem professors. So it's a number combination. So 6 choose 2 and 10 choose 2, and then I won't show the calculation, but you can certainly calculate those values separately, and we get 15 over 45, which is 1/3 or 33%. And so it's a 33% chance that if 2 professors are selected at random, then both of them will be a chemistry professor. And similar to that question, number 13, says a committee consists of 11 women and 10 men, so that's 21 total. And then 3 members are chosen as officers. What is the probability that all 3 officers are women? So that's our statement. Probability that we have 3 women officers. So again, in words, the number of ways that we can choose 3 women from 11 women, and our sample space is the total number of ways that we can select any 3 people from 21 people. So that's kind of what we want to look at. This is the desired event, which is here in our probability statement. This is the total possible outcomes for our sample space. So we have 11 choose 3, divided by 21 choose 3, and we evaluate that using the formula, and we get 165 divided by 1330, which is 0.12, which is an unlikely event. So these are some questions. You can expect the same difficulty level in your exam in eCampus. I urge you to kind of go through the video, watch the parts that you feel are maybe that you've struggled with more in the homework. Feel free to ask questions. If you are concerned, let me know if you have any questions. Just shoot me an email. I'll get right back with you.